So let's do a related friction problem where we're pulling a box along the floor and where there is friction. Instead of now having the force angling down, we're going to be angling it up since we've attached a string and we're now pulling in at a direction theta upward from the horizontal. So there are some similarities between the previous problem we did where we're pushing down and this one, but the main one is that the force F now resolves itself into an x component, F cosine theta, which is exactly what it was before, but the y component now, instead of pointing down, now it points up, and its magnitude is F sine theta. So the force diagram now is the following one, this one that you see right here. You have a downward mg balanced by an upward F sine theta and n. And then you have F cosine theta, which is the x component of the applied force. And impeding that is a frictional force pointing off to the left. And so from this picture, you can immediately see that the normal force is now less than mg. In the previous case, when we were pushing down, angling the force downward, n was bigger than mg. You can see it from the picture. Let's write a Newton number 2 in the y and in the x direction based on this force diagram. And so the y Newton number 2 is n plus F sine theta. Recall this is a minus in our previous case. Minus mg is equal to 0. And so if we solve for n, we get n is equal to mg minus F sine theta. And Newton number 2 in the x direction is F cosine theta, the x component of the applied force, minus the impeding force of friction, and that's going to be equal to the mass times the acceleration in the x direction by Newton number 2. Let's make these same assumptions we did before using a 2 kilogram mass, which would lead with easy numbers to a 20 Newton weight, mu sub s and mu sub k respectively 0.4 and 0.2. Let's assume the applied force has a magnitude of 8 newtons applied at 30 degree above the horizontal angle. And so we can now compute F sine theta as 8 newtons times sine 30, which is 4 newtons. F cosine theta, which is 8 newtons times cosine 30, which is 6.9 newtons. So these have the same magnitudes as they had before. The directions, however, are different. And so now our n is mg minus S sine theta, which in other words is 20 newtons. That's the weight minus the y component of this applied force, 4 newtons. And so the normal force is 16 newtons, 4 newtons less than the weight. The maximum impeding force of friction is going to be given by always mu sub s times n, and so that would be 0.4 times the n we just computed, 16 newtons, which is 6.4 newtons. And the applied force, the x component of the applied force is 6.9 newtons, and since 6.9 newtons is bigger than 6.4 newtons, the maximum impeding static frictional force possible in this case, a sub x is going to be bigger than 0 meters per second, and m will move to the right. And since it's moving relative to the ground, we now have to use mu sub k. And so recall in the last example where we were pushing downward instead of pulling upward, we were not able to get the object to move with this magnitude of force. But now that we're pulling up and decreasing the normal force, something different happens. Okay, so let's move up here where I've written down a sub x, solved for a sub x from this Newton number 2 equation in the x direction. And so a sub x is the x component of the applied force minus the impeding frictional force divided by mass. The x component of the applied force we've previously computed as 6.9 newtons over here. And please understand, since m is moving relative to the surface, if there's movement, you have to use kinetic friction. So I have the coefficient of kinetic friction here times the normal force, so 0.2 times 16, divided by the mass. So the numerator is the net force in the x direction, and the denominator is the mass. And so that's 6.9 minus 3.2, which is 3.7 newtons divided by 2 kilograms. And that comes out to 1.9 meters per second.